Hello, everybody. Happy Monday. Hope everyone had a good weekend. It was nice out. Hopefully, you got outside, did some things, had some fun. Today, we are going to finish up thermodynamics. We need to relate free energy and equilibrium. And this will be the last section of thermo. All right. So our free energy, or delta G naught, okay, this is at standard conditions. Right, well, most reactions don't occur in standard conditions. So if we are not at standard conditions, we can calculate delta G. Now it's just delta G, no delta G naught, right? Because we're not at standard conditions. So delta G is equal to delta G naught plus RT log Q. It's ln, sorry. ln Q. Okay, so this is our free energy, not at standard conditions. This is our free energy at standard conditions. R is our gas constant. And it's 8.314 joules per mole K. Right, but we need to be in kilojoules, so this will be 0.008314 kilojoules per mole dot K. T is temperature in Kelvin. And Q, if you remember, is our reaction quotient. Now, remember, Q is just using our equilibrium expression and throwing in the numbers that we're at. Okay, and we'll go through that one of those. Okay, so our Q is really just our equilibrium expression with the values that we have at the time. Now, if you remember our reaction quotient Q, if it's equal to our equilibrium constant, that means we're at equilibrium. If Q is less than K, okay, it will go forward. If Q is greater than K, the reaction will go in reverse. All right, so we're going to have to be able to calculate Q, all right, and we're going to do some different things here. Okay, now, in this equation, if delta G is positive, the reaction proceeds in reverse. If delta G is negative, the reaction proceeds forward. If delta G is equal to 0, that tells us that it's at equilibrium. Now, if we're at equilibrium, that actually changes this equation. All right. So if we are at equilibrium, well, if we're at equilibrium, we know that delta G is equal to 0. If we're at equilibrium, we also know that the reaction quotient is equal to equilibrium constant, KEQ. So we can rewrite delta G equals delta G0 or naught plus RT ln Q. We can rewrite this to, well, we know that delta G at equilibrium is equal to 0, so 0 equals delta G naught plus RT ln K, our equilibrium constant. We can rearrange this, and it turns out that delta G naught is equal to negative RT ln K. All right, and you'll need that equation. So at equilibrium, we can use this. Now, we can actually take this, because a lot of the time you're going to want to solve for your equilibrium constant. So we can manipulate this so to get K by itself. So K is equal to 10 to the negative delta G naught all over RT. Right, so mathematically, okay, these two are the same things. We're just rearranging things. So here we're calculating for delta G naught or delta G at standard state. And here it's the same equation. We are just calculating for our equilibrium constant. Now, if we look at this equation, okay, if we look at this equation, if K is greater than 1, let's write this down. If K is greater than 1, what does that make delta G? Okay, well, if it's greater than 1, delta G is going to be negative, which means the reaction will move forward. If K is less than 1, if our equilibrium constant is less than 1, that makes our delta G positive, which means the reaction will move in reverse. All right, so let's go ahead and try a couple problems. What is the delta G for the following reaction at 298 K given N2 gas is equal to 1.0 ATMs, H2 gas has a pressure of 2.5 ATMs, and NH3 gas has a pressure of 0.75 ATMs, and delta G naught, or delta G at standard state, is equal to negative 33.3 kilojoules. And our equation is N2 gas plus 3H2 gas goes to 2 NH3 gas. All right. So now we're calculating for delta G. So delta G so this is what we're calculating. We know this. It was given to us right here. Okay, this is a constant we know. It gave us temperature. We have to figure out the Q. Right now, the Q we're just gonna substitute into our equilibrium expression. So we're gonna have to calculate our reaction quotient. Okay, so Q is equal to the pressure of NH3 squared all over the pressure of N2 times the pressure of H2 cubed. Right, so to come up with our Q, all we do is we substitute in our numbers. Right, so this ends up being 0.75 squared all over 1.0 times 2.5 cubed. So our reaction quotient is 0.036. Right, so we need that. So now that we have that, now we can substitute into this equation. Right, so we're trying to find delta G. Okay, so our delta G at standard state is negative 33.3 kilojoules plus our R, and it's got to be in kilojoules. So we're going to use 0.008314 kilojoules per mole dot K. Our temperature is in Kelvin. It's 298. Okay. And ln of 0.036. So then we do all this math. Delta G is equal to negative 33.3 kilojoules plus a negative 8.24 kilojoules. So our delta G is equal to 41.5 kilojoules. Now, what does this tell us? Well, this is math. So we got negative 41.5 kilojoules. So what is this negative telling us? Well, the reaction would proceed in the forward direction. Okay, so we would go in the forward direction. So it would move from here to here. All right. Let's try another one. I got two more to do, and actually then we're done. Let's get a little more space here. Let's calculate the KEQ for the Haber process given delta G0 is equal to negative 33.3 kilojoules per mole at 298 K. Right? Now this is our same exact equation. Okay. N2 plus 3H2 goes to 2NH3. Now, we want to calculate our KEQ, which means we're gonna be at equilibrium, right? So since we're gonna be at equilibrium, we know some things. We know that delta G is equal to 0 and our Q is equal to our K, or our KEQ. So if we start with delta G equal to delta G0 plus RT LQ, okay, we've already done this. This is 0, right? This is K. So we end up with delta G0 equal to negative RT ln K. But we're trying to calculate for K, so to get K by itself, we have K equal to 10 to the negative delta G0 divided by RT. So now we can just substitute. Okay, so K equals 10 to the negative, which makes 33.3 positive, divided by R times 298. Okay, so if we do all this math, our K ends up being 6.87 times 10 to the 5th. Okay, and there's our equilibrium constant. Okay, just another way to use those equations. Let's do one more. The value of KEQ equals 45 at 298K. The Q, or the reaction quotient, at the same temp is 35. Determine the value of delta G naught and show which direction the reaction will move, and show which direction the reaction will move. Well, we're at equilibrium again. Okay, so at equilibrium, we know that delta G naught is equal to negative RT ln K. So our delta G is going to equal negative 0.008314 kilojoules per mole dot K times our temperature of 298 K times ln 45. So when we do this math, our delta G is equal to a negative 9.43 kilojoules per mole. So this is telling us that our reaction will go forward. Okay, that's all I got. I have assigned you a bunch of problems. Okay, so you need to go through. You want to make sure that all of your chapter 19 sections are done, and you want to work through your textbook stuff. All right, so this is the last day on thermodynamics. All right, so tomorrow we're going to go ahead and start redox. Okay, we'll probably spend, I don't know, probably about a little over a week on redox, and then we'll do our last unit. So we're moving right along. You need to stay on top of things. All right, so make sure you go through all those problems. All right, have a good afternoon.